There's a lot of words in this question at the start, but it's basically summarized by this diagram and the fact that we're doing projectile motion. So we're going to fire the ball and it's going to kind of go something like this. I've got some questions to answer. So for u equals 10, find the greatest height above the ground reached by the ball. It's going to be maybe here. I'm going to say I'm going from A to B, and I'm going to apply Suvat. Now we've got the horizontal component and the vertical component, but for the greatest height, we only need to look at the vertical component. So applying Suvat up, the initial velocity is going to be 10 sine 40, because it's like opposite the angle. If I draw my triangle here, this is the velocity I'm interested in at the moment. V is then going to be 0 because it's where it's like momentarily at rest. That's the maximum height. And A is minus 9.8. And we want to work out what S is. So the missing one is T. We can use V squared equals U squared plus 2AS. Therefore 0 is going to equal 10 sine 40 all squared minus 2 times 9.8, that's going to be 19.6 times S. Rearrange, S is going to be 10 sine 40 all squared divided by 19.6, which gives 2.108. Now just be careful, that is the maximum height above the starting point here, but actually we're asked for the greatest height reached above the ground. So we need to add on 1.5. So it's going to be 3.61 meters. On to part B, it asks us for the distance between the ball and the hoop when the ball is vertically above the hoop. So I'm now going from A to C. And we've got the horizontal part and the vertical part. I'm going to need to use both here because we were told that we traveled 6 meters. And U now is going to be 10 cos 40. We had the vertical component as 10 sine 40, but now it's like the adjacent that we're interested in, this one here. In fact, there's no air resistance, so A is 0 and V is actually 10 cos 40 as well. And this turns from Suvat really to just speed equals distance over time, or S equals ut in fact. The half AT squared is just going to be 0. So from that we can work out T. It's going to be 6 divided by 10 cos 40. And I can work that out before I move on. Okay, we could leave it exact, but as long as we work, it's probably a bit easier just to get it as a decimal. So 0.7832. I might just write down one more figure. Right, now let's go back to working vertically. So we want to work out what S is here. U is back to being 10 sine 40. A is back to being 9.8. But now we know the time from the horizontal part. It's going to be the same 0.78324. So for this, we don't know V, but we can use S equals UT plus half AT squared. minus a half times 9.8, that's going to be 4.9. Okay, I've got my answer stored here, so I can just times by that rather than typing in some of the decimals. Oh, and I should be squaring the time here. 2.0285. So remember what that is. That's actually going to be this whole distance here. And therefore, I need to add on 1.5 to get the amount above the ground, and then minus 2.5 to get the height above the hoop. So it's 2.023, sorry, 2.0285 plus 1.5 minus 2.5. That's equivalent to just minusing 1. 1.0285 or 1.03 meters. That's enough, but I wrote in my original answer the ball is 1.03 meters above the hoop when it's vertically above the hoop. Well, that's okay. Now asked to calculate the value of u, which would allow her to hit the hoop. So at the moment we're 1 meter above the hoop. We're going to have to same angle, but put in slightly lower velocity, like hit it about there. So I'm going to call this point D, and we're going to have a look at A to D. I'm going to do this from first principles, like i.e. not using just any formula given, but then afterwards I will talk about how the mark scheme allows you to do it a bit quicker. I personally quite like my way because it doesn't require you to just memorize a formula, and it's how you get to the formula as well. So this is going to work out in a very similar way to part B, in fact. Starting out to the right, we're going 6 meters. Now U is going to be capital U cos 40. And that capital U is going to be less than 10. That's what we're trying to find. B is then the same because A is 0. And we're going to get T in the same sort of way. T is going to be 6 divided by U cos 40, leaving it exact this time. I've used S equals UT. I've just kind of skipped a few bits because it's the same idea as up here. Then vertically, right, now this time, in order to hit the hoop, remember we started here, so we want to go up 1 meter exactly, because that's how far the hoop is above our starting point. That's very important. Got U sine 40 and A is minus 9.8. So again, we can use S equals UT plus a half AT squared. 1 equals, okay, but here's, oh yeah, sorry, I forgot this bit. We can now use the T from the horizontal part, 6 over U cos 40. So we're combining the two into, yeah, into the single equation. So we're going to get U is U sine 40, but then we're going to be times them by 6 over U cos 40, And I can put the 6 here. And then it's going to be minus 4.9 times 6 over u cos 40 all squared. So the u's cancel, and I've got 1 equals 6 tan 40 minus, I need to square the 6 to give 36 and then times that by 4.9. Which gives 176.4. I'm going to leave this in terms of cos squared 40. Now I just need to rearrange to make u squared the subject. So 176.4 over u squared cos squared 40 is going to be 6 tan 40 minus 1. I can times by cos squared 40. Any point you might just want to put some of these in your calculator, but I'm actually working exact at the moment. And I just realized, sorry, this is still 1 over u squared. So if I want u squared, I'm then going to have to divide through, and it's going to become 170. So, right, I'm going to times through by u squared cos squared 40, and I'm going to divide through by everything. So I end up with u squared on one side, and it's going to be 176.4 divided by all of this. 74.50. So u is going to be the square root of that. 8.6316. Or 8.63 meters per second. Nice one. Now, I did hint towards this, I'm just going to say it now. You could have just quoted this formula, and this is the general formula for when you are going from a starting point to a point x, y. So we could set y equal to 1 and x equal to 6 and theta equal to 40, g equal to minus 9.8, and you would get exactly the same equation that we got, where is it, like down here. Okay, so that's a shortcut. It requires you to learn the formula. It's going to save you a bit of time, I guess. That's the advantage. The disadvantage is, like it's important to be able to do it by first principles like I did. So it's not taking that much time. I just want to sort of say that you can go either route. Now, finally, we're asked a couple of modeling questions. How appropriate is the model for predicting the path of the ball when it's thrown by the girl and suggesting improvement? So I went with air resistance for both of these. I said it's not very appropriate because it ignores air resistance. And then I said for part D, we can include air resistance. Here's some possible other answers. So relies throwing at a very precise angle and velocity. Not too keen on that one. Air resistance I mentioned, so it's going to fall short. The target is actually a ring, so it's not a point in space. That's a good one. So she has some flexibility. It might hit the outside and bounce in, for example. Um, and then how could we improve it? So yeah, if we'd have to include it as a particle, the angle could be a variable. Suppose, yeah, we could change the speed and the angle. Angles and velocities could be given as ranges, and the hoop could be modeled as a line of points. So something along these lines. Other ones should be accepted as well. But that's it for this question.